you are doing well. Things are starting to dry out a little bit on the smaller creeks and tributaries, but they're continuing to get deeper and deeper on anything that's under the influence of the Ohio River. I had to drive through a couple of inches of water to get to work today and flew the drone around to look at some of the flooding. Pretty interesting. I plan after class to go check out the riverfront park. I heard that they were putting in the flood wall gates there, so that's kind of exciting. If you've never seen those before and you're in Huntington, might go check out something engineering and even hydraulic related. Let's begin with a couple of announcements. So first of all, Monday is the big day in this class because you've got homework 6 which is due, and then also the first midterm exam. And I've announced this before, but let's just go over the details. That on Monday what will happen is that at 12:30 the exam PDF file will be available on Blackboard, and so you can print that out or just view it on the screen, and you'll do your calculations, some of them by hand and some of them with Excel, and by 2:30 p.m. and not after 2:30 p.m. you need to upload both your scanned PDF file and the Excel spreadsheet to Blackboard. And so at 2:30 that availability will close, and I won't accept any late submissions, and I won't accept any submissions by email. Now during the test you shouldn't refer to any websites or collaborate with any people, but you can use your textbook, your notes, my notes, meaning the lecture slides, your previously solved homework assignments and examples. So it's I think pretty relaxed opportunity for you to do well, considering the length of the exam is still going to be a 50-minute test even though you've got 2 hours. So you've got more than double time, and you're allowed to use this wide range of resources that ordinarily wouldn't be available in a typical semester. So I look forward to everybody really nailing it on this test, and there's no reason why you can't. I don't throw curveballs just for the sake of being sinister. These questions are all going to be very closely related to the homework and examples that you've seen before. So if you've been keeping up, then everybody should do just fine, and if not, maybe a little bit less fine. So any questions about these announcements before we continue talking about pumps? Okay, well, you know, if something does come up as you're studying, feel free to contact me by email or Teams or call me on the phone. I'd be glad to help you. All right, so we're going to talk about the affinity laws, and then if we have some time for additional practice, we'll take a look at the nodal method one more time. Okay, now affinity laws, sometimes called scaling laws, are a way to figure out what happens when you change some parameter that's associated with a pump. Pumps often come in families or have parts that are replaceable and interchangeable. And so, for example, a pump designed from a manufacturer may have different sized impellers that can be put into the pump. The impeller is that spinning blade that accelerates the fluid and gives it additional pressure. And so inside of this pump housing there may be one impeller diameter that's, let's say, 3 inches, and another one that's 4 inches, and another that's 5 inches, and any one of those sizes could fit into the same housing. It's just that they have a different size, and therefore the performance of the pump is going to be different depending on which diameter impeller you have inside of that housing. Another common illustration is that most pumps are originally designed to operate at a certain RPM, but you can add a variable frequency drive, and with that you're essentially changing the frequency that the electricity is going into the motor. Rather than being 60 hertz, if you give the electricity at 50 hertz, then it's going to slow down the motor, and therefore that's going to reduce the rotational rate of the pump. And so either one of those things is going to change the original performance that you had. And remember that what we looked at on Monday and Friday of last week is that you combine pumps with the system curve to find the operating point. So what flow rate you're going to get out of a pump depends how much work is the pump doing and what force is it working against. You know, how high does it have to lift the water, and what is the frictional losses in the system that the pump is trying to overcome. And so, you know, how much effort it has to do kind of is going to reduce the flow rate the more and more cutoff head that it has. System curve equals pump curve, and you solve for the flow rate and determine the operating point. But you can have a different pump curve if you take one of these pumps and you change something about it. And so the calculations that we're going to do today rely on these relationships that have been defined that explains, you can think of it as before or after. You can think of it as pump number 1 and pump number 2. But these related pumps, which have similar characteristics, if you change 1 or 2 parameters, you can use these scaling laws to determine what is the updated performance curve for the pump. And so, by the way, this format of the scaling laws is what you will find in the FE reference manual. And so our textbook uses slightly different notation. You know, for example, here the capital H, that's the term and the variable that's used in the FE reference manual, but I think our textbook version of this would call that H sub P. It just means pump head in either case. I just wanted to point out that here I've used the FE reference manual symbology just so that you can get acquainted with that. Okay, so in pump number 1, there's a relationship between the flow rate, the rotational speed, abbreviated here as N, and the impeller diameter, D. And so what you notice is that if you have pump number 1 and pump number 2 and they're different in some way, then the flow rate that you can achieve with pump number 2, so Q2 would mean the flow rate that you're going to achieve with pump number 2, depends on the rotational speed and the impeller diameter. And so for each one of these, in a problem statement, what you'd typically be given is you'd be given, you know, for your first pump, we already know for the first pump what its performance curve. And we already know what's the diameter of the impeller on that first pump. And its intended rotational rate. So all these things are already known about the first pump. And the second pump, we also know how its diameter may be different and its rotational speed might be different, or it might be the same. But with this first equation, we're going to find a relationship between the flow rate in one pump to the flow rate in another. So this will just be one equation that we substitute into the performance curve. And you can see that depending on what's given in the problem statement, like maybe instead of on a volumetric basis, which is Q, maybe what you have is a pump performance curve that's describing this pump's mass flow capacity. And so you'll notice here the second equation is essentially the same thing as the first. It's just that if we have mass flow rate and divide it by density, that's volumetric flow rate. So these first two are essentially the same, but related. This next one is important because it is how you're going to define the relationship between the pump head from the first pump and the second pump. And so H1 would be the pump head that you get out of the first pump. H2 is what you get out of the second pump. And so in the first example we're going to work today, we're going to have an example where we know the rotational rate, the diameter, the flow rate that will come out of that for a certain pump head. And so we'll use the first equation and the third equation just based on the variables that we're given. Good question. Gavin asks, are N's units RPM? You can use RPM, you can use revolutions per second, because it's going to be a ratio. So as long as what you'll eventually do is you'll move this N over to the right-hand side of the equation and the D to the right-hand side of the equation. So as long as for both pump 1 and pump 2 you use the same units, then it can be inches, centimeters, RPM, radians per second, whichever, as long as you're consistent in the numerator and the denominator. Great question. And by the way, so what that means is that these same scaling laws can be used for both traditional units and SI units. So there's not a different set of scaling laws that's used for SI. Okay, well, let's look at a specific application of this and just give you a sense of how calculations like this are accomplished. So we'll go through the first one together, and then I have two more that I'd like you to attempt working in the breakout rooms. Okay, so here in this first example, what we know is we've got a certain pump that normally we spin it at 1200 RPM. It's using an 8-inch impeller, and this is its performance curve. So let's just try and remember what the physical significance of this performance curve is. It has a cutoff head of 12, and I guess since we were given the impeller is inches, let's assume that that's 12 feet. So the maximum delta Z that it can overcome would be 12 feet. That's how much pump head this pump can add. But that is at a flow rate of 0. And the faster the flow rate is moving, there's less and less pump head that it's adding. So it can add a lot of pressure at a low flow rate, or it can add a little bit of pressure at a higher flow rate. So that's just kind of how these pump performance curves operate, is you have the cutoff head, and then you subtract out that maximum head is going to be reduced based on what the flow rate is. Okay, so now back to the affinity law. We want to find out what if, instead of spinning it at 1200 RPM, we start to spin it at 2400 RPM. Okay, so let's just first take stock of what variables we have. We've got N, the rotational speed. We've got D, the diameter. And in the first case and the second case, the diameter is going to be the same. So here in statement A, it doesn't say anything about a new diameter. So D1 and D2 are the same. N1 is 1200, N2 is 2400. And then we've got the pump head for situation 1. So this would be H1 and this would be Q1. We want to find out what is H2 and Q2. In other words, what's the equation for the new performance curve? Here's our first performance curve. But what if we are spinning it faster? What will be the updated performance curve? So looking over here at the scaling law options that we have, we're going to use this first row and the third row because these are the variables that exist in our problem statement. Okay, we haven't got anything asking about power or the pressure rise, and so we discard the bottom two. And the flow rate is on a volumetric basis, so we use the top one but not the second from the top, which was mass flow rate. Okay, so let me just show you how the calculations work out on something like this. I'll bring up my solution here just so you can get the initial idea, and then I'll turn you loose into the breakout groups for the next one. All right. So just defining the variables. N1, the rotational speed of the first pump, 1200 RPM. The diameter of the first pump is 8 inches. And then I've translated the performance curve. Here the performance curve said H sub P. Well, H sub P is pump head as our book calls it. But pump head, as the FE reference manual calls it, the variable for pump head is just H. So I've rewritten that as H. So the pump head for the first pump is 12 minus 0.01 Q1 squared. So the flow Q1 just means the flow rate in the context of that first pump. All right, so we want to know what if we spin it twice as fast. So that means N2 is 2400. The diameter didn't change. And with the first scaling law, we can find out what is the ratio of the flow rates. And so look what I've done here. Just starting with the given scaling law, I've eliminated the D terms because D2 and D1 are the same. Since there's no change, D1 and D2 can be omitted from this simplified scaling law. Okay, so what's left is that the ratio of the flow rate of pump 2 and the rotational rate of pump 2 is equal to the flow rate of pump 1 and the rotational rate of pump 1. So in other words, if we solve for Q1 in terms of Q2, we get here in the box Q1 is 0.5 Q2. So the second pump can achieve twice the flow rate since it's spinning at twice the speed. Makes sense so far. That wouldn't have been the case if there was a change in diameter. It wouldn't have been that kind of linear relationship like it is so far. Okay, but the next step is we need to find out how does the performance curve change? Okay, so from the second of our two scaling laws that we're using, we get the relationship between the pump head of this new pump, pump 2, compared to the pump head of the first pump. And so we're going to be solving for H2 in terms of H1. Because with this first one, with this, we're going to substitute in here. So where it says Q1 from our existing equation, we're going to substitute in 0.5 Q2. Now, we want to find out what should we substitute in here for H1. We want to know what factor will H2 be. All right, so going back to this earlier law, it's this third one here in the middle that has the relationship between the pump head. So I've just rewritten it here. The diameters again are the same, so we can cancel that term out. And so our simplified scaling law, once we omit any relationship of the diameters, is that the head of the second pump divided by the rotational rate of the second pump squared is equal to the head of the first pump rotational rate of the first pump squared. All right, so rearrange that to solve for H1 because that's the substitution. I want to substitute something in here to the original curve. I want to substitute in something new so that I can get H2. So how does H2 and H1 relate? Okay, so H1 is a quarter of H2. When it spins twice as fast, you're going to get 4 times as much pump head. Okay, so double the flow rate and 4 times as much pump head. So we substitute those two things into the original performance curve. And here we've got it. Remember, the original performance curve said H1 is 12 minus 0.1 Q1 squared. So just substitute in our H2 factor in terms of H1 and our Q2 factor in place of Q1. And so the ultimate new performance curve is that it's 48 is the new cutoff head that it can achieve. And so we can make changes to any one of the parameters and predict what this pump is going to do in different circumstances. All right, so that's what I'd like you to attempt when I put you into the breakout rooms now for this, this next question. What is the performance curve if the original 1200 RPM motor is used, but now you switch to a 10-inch impeller? So D is going to be changing. You're going to be changing D, and so D is a term in both the first and the third, but the rotational rate N is going to be 1200 for both of them. Okay, and then question C is kind of an interpretation thing here. If you need to pump it 30 feet above the source, which option is best? This original pump performance curve, working it at 2400 RPM like was described in question A, or operating at 1200 RPM and using the larger 10-inch diameter. Okay, let me push you to the breakout rooms and take, I think we've got about 10 minutes that you can spend working on this. Essentially, in the end, what we want to see is what is the new H2 in terms of Q2 when you change the diameter. Okay, so part B is asking, what if we have the original motor, 1200 RPM, but a larger impeller? So we're going to change D in both this first equation and the third one, but N will be the same for case 1 and case 2. All right, so here, starting off with the relationship that defines Q1 and Q2, you can see the substitutions that we've made, and what you ought to get is that Q1 is less than Q2, 0.512. So we want to know Q2, we want it this way so that we can just drop this number into the original performance curve. So our original performance curve has Q1 in it. So here's our original pump performance curve. So we want to just be able to substitute what is the equivalent value of Q2 into that location. Okay, so then the second scaling law that we use is the ratio between the pump head and the rotational rate and the diameter. And since the rotational rate is the same for both the first pump and the second pump, then all that changes here is the diameter. So you should get now H2 in terms of H1. And then we can put that substitution into our original performance curve. So you can see that we now have H2 substituted where H1 was. And then the tricky thing is you can't forget the squared term, because what's inside of the parentheses here, the 0.512, that's going to need to be squared before we multiply it by this first term. Okay, so in the end it's 18.75 minus 0.04096 Q2 squared. Okay, now the last question is asking if you need to lift water 30 feet, which is going to work? And that's a conceptual question. This part C is not really a calculation question. What it's asking you to do is remember what is the intercept of a pump performance curve. And so our original pump performance curve has an intercept of 12 feet, which means the maximum amount of head that pump can add is 12 feet. And if we need to lift water 30 feet, 12 feet of cutoff head is not going to work for us. You'd turn on the pump and it would be spinning, but it just wouldn't be giving enough energy to lift the water. So this original pump performance curve doesn't work. The question A, where it was 2400 RPM, remember that its cutoff head was 48 feet, so that will work. And the second situation that you just worked, also that's cutoff head is below 30 feet. And so, you know, as far as selecting the correct situation to lift the water 30 feet, what you'd need to do is you'd need to go with the 2400 RPM rotational speed and that original 8-inch diameter impeller. Now we could have changed both things simultaneously. You know, I could have asked you, what if we switch it out with a 10-inch impeller and we rotate it at 2400 RPM? So, you know, these scaling laws will allow us to adjust multiple parameters at once. Okay. Now, I just emailed you a PDF file that is a quiz that I gave in a previous semester. We don't do quizzes this semester. Just because, you know, like the struggle of administering it remotely and then having it be a reliable instrument, since I can't really enforce any sort of non-collaboration rules. We haven't had quizzes this semester, and we're not going to. But if you are interested to see what I would have asked you today if we had a quiz, it's this additional practice nodal method PDF that I just sent you. So this is something that by now you should be able to solve. And you know, this is significant because you've got your first exam coming up on Monday. And so if you're wondering what's the kind of question you could expect to see on the exam, this is a sample exam question, essentially. And so remember, the nodal method allows us to figure out the distribution of flow when at a node the flow is branching. So here we know the the flow through pipe A is 0.15 cubic meters per second, and then it branches. Some of it will go through pipe B, some of it will go through pipe C. And just to simplify, I've said that you can assume the F value. That way you don't have to calculate it. Local losses can be neglected. But what you do have for each pipe is its length and diameter. Now on the first page is some equations. And remember that what we do for problems like this is we set the head loss due to pipe friction of one pipe equal to the head loss due to pipe friction through the other. And so you're going to be using this Darcy-Weisbach equation. But the more useful form of the Darcy-Weisbach equation, instead of doing it in terms of V, the more useful form of that equation is H sub F is F times L times Q squared divided by D2G A squared. So let me just pause for a moment. I'm not going to put you in the breakout rooms. Let's pretend like this is a quiz and you're a deer in the headlights and have to think quickly now and set this up. How would you set this up to solve for how much flow goes through pipe B and how much flow goes through pipe C? So again, the key here is you set H sub F through one pipe equal to the H sub F through the other. So that's the first equation. And then the second equation is that the two flow rates together collectively equal 0.15 cubic meters per second. So that's continuity. Two equations, two unknowns. All right, well, let me pause for a second, give you a chance to dust this off in your memory. See if you can remember how to solve for the two flow rates, because this is exactly the kind of question you can expect on Monday. Okay, so maybe you haven't crunched all of the numbers yet, but at the very least, I hope this was enough time so far for you to set it up and identify the correct solution strategy that's needed. So let's look at what you do for this one. Since we've only got a couple minutes left, I want to show you the setup here. So, okay. All right, off to the right of this second table, I've calculated the cross-sectional area for pipe B and for pipe C. And that because the concept here is that when the water is flowing from node X to node Y, regardless of whether it goes through pipe B or whether it goes through pipe C, it has to have the same amount of energy loss. You couldn't have a different amount of energy loss, because then that would be like saying that 3 is equal to 2. You know, you have to have the same loss. It's the analogy of skiing down the mountain. Remember, if you take the steep path or the less steep path, you're going to end up at the same spot that has the same elevation regardless of the route. So that's the analogy here. So we set the two head losses equal to each other, and then you just kind of substitute in all of the known parameters here. So the friction loss factor, the length of each pipe, its diameter, the cross-sectional area, and so on. So in solving for that, we get a ratio that the flow through pipe B is more than the flow through pipe C. It's 2.67 times. And let's see if that makes sense. Like, what is it about pipe B that would make it for more flow to be going through there? And it's because the diameter is significantly larger. You know, the length is more, so there's going to be a little bit more head loss due to that pipe length, but it's more than made up for by this larger diameter. And so there's more flow going through B than there is through C. So now we have the relationship of QB in terms of QC, and that's the first of the two equations we use, the second being continuity. So here's the continuity equation that says the sum of the two is 0.15, and when we substitute this first relationship into continuity, and we can solve for each of the flow rates. And so QC would be 0.041 cubic meters per second, and QB would be 0.109. Now the second part of this question was, what's the pressure at node Y? So to find the pressure at node Y, you can either use pipe B or pipe C. So we know the pressure here at junction X, and so the pressure at Y will be however much pressure there was at X minus the head loss effect. Okay, so in case you later on go through and do the calculations for that, let me just give you the solution in its entirety here. It'll be in the video, or you can just look. So we take one of the flow rates that we've just solved. Here I've done QB, and I substitute it into the head loss through pipe B. So there's 34.91 meters of head loss. And so that's the magnitude of the head loss in terms of head. In terms of a pressure change, then we want to... The recording stopped. Well, I'm still recording on the YouTube. Anytime I push you guys into the breakout rooms, the Blackboard recording stops, unfortunately. Okay, so we find out how much head was there originally. At X, there was 57 meters of head. We lose 35 effectively through the pipe. And so then that means there's 22 meters of head remaining. And in terms of pressure, you multiply that by the unit weight, and the pressure downstream will be 222.5 kilopascals. All right. So in a normal semester, you would have gotten that as a quiz, but today you're just getting it as dessert, I guess, after our walk into the affinity laws. So looking at the announcements, remember that Monday is the big day for the course. That's when we're having our first exam, and homework 6 is due. So that's it for today. When we get together on Friday, we're going to be talking just about the design project. So you definitely do not want to miss that. The design project is worth a huge amount of points, and so it's important to get all the details for that. So I'll see you on Friday. Hope you have a good one. Take care, everybody.